Okay, it's time to look at some examples and problems related to section 8.5, the differential amplifier with an active or current source load. Okay, so with that in mind, let's move ahead to slide number. Okay, I gotta move this. Slide number 59, where we have the first uh, numerical. Now, unfortunately, I noticed that in the textbook there are no examples for this section. Uh, so I can't tell you here's an example, read it yourself. But there are some exercises with the answers given, so at least we can start with that. So there's exercise 816 on page 644, which is the first numericals related to this topic of a MOS differential pair with an active load, as you can see in the picture, in the circuit drawing here. So what is the question? An active loaded MOS differential amplifier of the type shown is specified as follows. So you're given W by L N for these two transistors to be 100, W by L P for these transistors to be 200, mu n COX equals twice mu p COX, so that makes it matched, right? That's 0.2 milliamps per volt square. And then VA, the early voltage, is given to be 20 volts both for N and P types. And I, the bias current, is at 0.8 milliamps, and RSS, which is the voltage across the bias source, the resistance of the bias source of this, whatever is creating this, it has a natural resistance RSS of 25K. So given all this information, we are asked to find GM, which is the overall short circuit transconductance, as it's called. Then we have to find RO, the output resistance, as seen from the output terminal, shown here as VO. Then the A differential, that means if the input is applied differentially, the gain for that. Then ACM, that means any common mode voltage applied to both ends, then that is way ACM. And finally CMRR. So the answers are given, but you have to obviously work through it. Alright, so what are the essential formulas? We want GM, right? So GM is here. GM is nothing but small gm for 1 and 2. But small gm has this formula, 2I by VOV for any transistor. What is ID? ID is half of I. ID can also be shown to be this. And why do we need W by L? Oh, we'll need it for later. So you can figure out, well, W by L is given, so we can figure out VOV from here, right? Okay. Then you need the output resistance RO, so that's the parallel combination of RO2 and RO4. You need GM3 because you need GM3 here in the formula for the common mode gain. And then of course CMRR is AD by ACM. Okay. So those are all the various formulas that we need. So here we need to find VOV to put in the denominator here, right? To find GM. All right. So those are the various formulas that I could think of that we need. And let's look at my famous PDFs with the solutions. This one is called Chapter 8 Differential and Multistage Amp Part C. So this is Part C. Next section I'll do Part D. And here are all the class problems. So this is exercise 816. So first of all, ID is half of AI, which is 0.8 milliamps given. So ID is 0.4 milliamps in each. So in all these problems, uh, if they don't say anything, you can assume that these are all perfectly matched transistors and that the current splits equally between them and so on. So anything that makes our job easier, it's okay to proceed in that way. So ID also has this formula, as I just said. We are given K prime into W by Ln. This whole thing is given, right? Well, K prime is given to be Kn prime is 0.2 and then W by L is 100, right? So that's why I put 0.2 and then that's milliamps, right? And then 100 is W by L and then VOV square. So from here, if you solve, you should get two values for VOV because it's a square. But actually, you'll only get one value. It's not a quadratic equation. It's just a straight square root is what you're going to get. So 0.04 and then the square root of that is 0.2 is what you should get. Then GM1 or 2, when I write like this GM1 comma 2, it means it applies to both 1 and 2 transistors. 2ID by VOV, which is this, which comes out to be 4 milliamps per volt. So we know from our formulas GM is nothing but GM12, which is 4. The intrinsic resistance of the N type, which is RO2, right, this transistor, is VA, the early voltage, divided by ID for the N type, which is 20 by this, which is 50K. RO4 is really the same thing because this is also given to be 20. So 20 by 0.4, which is 50K. So you have 250Ks. So the output resistance, which is the parallel combination, is just the half of it. So that becomes 25K. Finally, well, AD is this, right? GM into RO, so 4 milliamps into 25 kilo ohms, that gives you 100 V over V. Now GM3, we have this formula. I was too lazy to write it, but you can see GM3 has this form. So if you substitute all those values, you should get 4 milliamps per volt for GM. Okay, which is I think no different from, yeah, which is what we got here also. So everything is the same, so it shouldn't be any different. Now a common mode, use this formula, 1 by 2 4 milliamps per volt times RSS, which is given luckily. Sometimes they don't give you, then you have to use a formula to find it, which we'll look at in another example. So this comes out to be 0.05. So you'll notice that ACM should generally be very low, right? So 0.005. Comparatively, if you look at AD, it's 100, right? So for CMRR to be high, the denominator has to be pretty low. Otherwise, it's a pretty useless differential amplifier, right? It is supposed to magnify or provide a very low gain for common mode signals. That's why all these denominator values you'll find to be should be low. Alright, so to find CMRR, you just do AD by ACM. Sometimes ACM is shown with a, well, I'm showing it in absolute value, but otherwise ACM should be a negative. There should be a minus sign here. I'm sorry if I missed that. Okay. Well, I'm only showing absolute value. But otherwise just plain ACM, if I ask you in a question in a quiz or something, make sure there's a negative value there. Then once you get CMRR in absolute value, to find it in dB, you just do 20 log this. So this, your calculator should be able to do this, and it's 86 dB. Okay. All right. So that was an exercise, and I think all the answers matched with what we have here. Next, we look at a problem 885 from the back of the chapter. In a current mirror loaded differential amplifier, again same drawing, all transistors are characterized by K prime W by L. So here he has given K prime W by L together as 4. Sometimes they'll give you just K prime separately and W by L separately, like I think in the previous example. Yeah, this is K prime, right? Mu n COX is Kn prime. So that's given separately, and W by Ln is separately. But here he has clubbed it into 2. And VA is given to be 5. So this VA, when it's like this in absolute value, it applies both for N and NMOS and PMOS devices. Find the bias current I for which the gain AD is 20 volts per volt. That means VO by VID should be 20. So here it's kind of the reverse. Instead of asking us to find gain, he has given us gain and says find I, the bias current. So that's the only tricky part here. So AD is given. We can find RO2, RO4 in terms of I. GM can be found in terms of ID. And we know ID is equal to half of I. So it shouldn't be difficult to solve for I. So let's see how that's done. 885. Using GM12 equals this. So GM12, we know all these values. I is the only unknown. So write that in terms of I as root of 4I, which is 2 root I. And this is milliamps per volt. So make sure you understand that it's milliamps per volt, because this is given as milliamps per volt. So it's easier sometimes not to worry about the decimal or the power, which will be, this is to the power of minus 3, this is to the power of minus 3. If you ignore that, you can simplify the formula a little bit, but you must remember that this is still milliamps per volt for GM. RO2 equals RO4 gives you another expression in terms of I, stand by I. Now gain is 20 given, which is, so RO2 in parallel with RO4, right? That's what you need. So that is half of 10 by I is 5 by I. Make sure you didn't miss that step. So that 5 by I is used here in this formula, and this other 5 by I is the GM. So the formula is GM12 RO2 in parallel with RO4, right? Sometimes that's written as capital GM, capital RO. Either way, you have a formula for AD with just one unknown, which is root I. So from here you can solve for I equals 0.25 milliamps. Okay. So basically what you'll notice in all of these problems is that the same formulas keep appearing again and again in different versions. I think the problems in this section, in this chapter generally are pretty easy. There's not a whole lot of trickiness involved. Uh, Make sure all these formulas you become familiar with, these formulas and these formulas also, and of course the definition of CMRR, gain differential, gain common mode. So if you have a good understanding of these formulas, you should be able to, do well on these problems. All right. So next I'm moving on to the next problem. And remember I had given you a brief introduction to Wilson current mirrors, which is nothing but a current mirror but with an extra single or two transistors on top to give the cascade effect. And what happens is the output resistance RO, which previously we just took as RO2 in parallel with RO4, now it's slightly more complex. Just for the current mirror itself, the RO has gone up. So you need to be able to put that into the final solution. So what do I mean? So let's look at this problem that uses a Wilson mirror to create I. Okay, so the bias current is coming using another current mirror. So there is a current mirror on the top here, which is the load. But the I generally so far it's just been given to us, right? We didn't worry too much about how exactly it was created. But we know that currents, reference currents, are also created by current mirrors. And here we are given the details behind the current mirror. Now it looks a little scary, but actually the problem isn't all that difficult. So let's see how to proceed. So consider an active loaded differential amplifier such as that shown here, with the bias current implemented with the modified Wilson mirror. When you have two transistors here and the cascading, it's called a modified. If you only have one transistor, it's just the regular Wilson mirror. Okay, so that's what he means by a modified Wilson mirror. And I is 200 microamps. So that I is this I. So the I is also given. So really there's not much we need to calculate with regards to the Wilson mirror. Now the transistors have Vt is given, the threshold, and this K is also given. What is the lowest value of the total power supply? That means this power supply and this power supply that allows each transistor to operate with DGS greater than VGS. So every one of the transistors has to operate with this condition called, shown as VDS, drain to source, is greater than gate to source. Now, isn't this saturation? This is the definition of saturation, right? Because VGS is VTN plus VOV if it is an N type. Now, VDS is greater than VGS. That means VDS is definitely greater than VOV, which is normally how we define saturation, right? VDS has to be greater than V over drive voltage. So if VDS has to be greater than VGS, now VGS is VOV plus something, right? Plus a little 0.5. So VDS is automatically greater than VGS is the condition for each transistor. So all the transistors are in saturation. So one of the formulas to use is this, because we have to find VOV. It's not given. And then this VDD plus VS, it has to be, if all transistors are in saturation, then each one of them has to have a voltage greater than its own VGS, right? So those are the two big formulas I thought were important to solve this problem. So let's look at, oops, did I miss something? Problem 488. Yeah, I think I may have reversed pages 3 and 4. So I apologize. So this should be page 4. And this should be page 3. Okay, sorry about that. So let's start with page 3 first. So for Q1, Q2, Q3, Q4, assuming the same current is everywhere, I by 2 gives you this. So 0.2 milliamps by 2 gives you this, so gives you VOV of 0.2 volts. Now VGS in every case has to be VT plus absolute value of VOV, so that's 0.7. So that is for these. Now for the denominator, not the denominator, for the Wilson current generator, Q5, Q6, Q7, Q8, ID is also 0.2 milliamps, right? Because the same current flows through this and this. Remember, you don't need to do a divide by 2 here, because the definition of the Wilson current or any current mirror is that whatever is in the reference here, or if this is the reference, then the other current, assuming they are all matched, is the same, right, is equal. So ID is 0.2. Not here we took 0.2 by 2, here it's just 0.2. So 0.2 gives you this. So the VOV for these transistors is different, and it's 0.28. Here the VOV was 0.2, here the VOV is 0.28. So the VGS of these transistors is 0.78, right? Now go back to page 4. So VDD plus VSS has to be DS4 plus DS2 plus DS7 plus DS6. So if you look at one branch here, 4, 2, 6 and 7, right? So if DS is at least equal to VGS, then this VDS plus VSS has to be 0.7, 0.7 and then 0.78 plus 0.78. So you get a total of 3 volts approximately as this sum. Okay, of course this will be positive, VSS will be negative, but because you generally do a VDD minus VSS when you do your formulas, so that minus of minus becomes flips to plus. But he's only asking us for VDD plus VSS. He's not asking us to separate the two. And this is the answer. Okay. All right. So that was 888. Next, I have a problem that for some reason I didn't find it in our chapter end, so I had to call it a unique name, and it's called problem MOS CMRR. So it's the first time where we are being asked to find CMRR. To find CMRR, you obviously need to find AD and ACM. And in this case, RSS is not given, so we have to use a formula to find RSS. But everything else should be pretty straightforward, what we have seen. Okay. So again, current I is 200 micro. All transistors, the VOV is given. That makes it easy because finding I becomes easy. Well, I is given. All right, let's see how we proceeded. Oh yeah, we need, okay, let's see. Then we need, GM, RO, AD, RSS, ACM, CMRR. Simple problem, not too difficult to comprehend. But let's see how we do it. So to find GM, yeah, I didn't show you the formula for GM12, but to find GM12, you need VOV. That's why VOV was given. All right. So AD is GM-RO, ACM is this formula with a negative, right? So GM is GM12, capital GM is small GM12, which is this, which is 1. RO, the output resistance, is a parallel combination of RO2 and RO4, which comes out to be, each one comes out to be 50K. So if you take the parallel combination, you get 25K. Thus, AD, using this formula, 1 into 10 to the power minus 3, 25 times 10 to the power 3, because this is kilo ohms, so milliamps, it comes out to be 25. ACM, using this formula, now GM3, GM2, GM1, they're all the same, which is this 1 milliamps. RSS uses this formula, the early voltage by I, which is 25K. So ACM, substituting into this, you get a minus 0.02 volts per volt. So you can see ACM is much lower than AD. So CMRR is AD by ACM, 25 by this, so it's 1250. Or if you take it in terms of decibels, it's 20 log of this, gives you 61.9 dB. Okay. Alright, again I apologize, the pages 3 and 4 got mixed up, so hopefully it won't confuse too much. Let's move on to one more. How many more do I have? Okay, this is probably the last problem on MOS. Then I have a few problems on BJT differential pair. Okay. So what is different or special about this problem? An active loaded NMOS differential amplifier operates with a bias current I of 200 microamps. The NMOS transistors are operated at VOV of 0.2, the PMOS devices at VOV of 0.3. So in this case, there are two different VOVs. That's one difference. The early voltages are also different. For NMOS it's 20, for PMOS it's 12. This is VA, right? Yeah. So given this, find capital GM, RO and AD. Also, for what value of load resistance is the gain, this gain AD, reduce by a factor of 2. So here we are not being asked to find CMRR and all that, but we are just told that once you connect a load like this, like I showed here, then the gain drops, right? So what load value will reduce by a factor of 2? Factor of 2 means half, right? Okay, so here are the formulas we need for AD. To find GM, you can do this. Then RO, you can find like this. Now remember, VAP is different from VAN in this formula, in this example. So you have to watch out for that. Okay, so let's see how to proceed with example 891. GM, you find like this, comes out to 1. RO is a parallel combination of RO2, RO4, which is this and this. That comes out to be, now, yeah, here it's a tricky business, right? Because normally we have just assumed RO2 is equal to RO4, but because he has given us different values of VAN and VAP, you need to watch out. I is the same, but VAN on the numerator is 20 here, VAP in the numerator is 12 here. So you get RO2 is 200K, RO4 is 120K, you take the parallel combination, you get 75K. So AD is this, 75. The gain, differential gain is 75. So one thing I want you to notice is, normally for single transistor amplifiers, MOS amplifiers and MOS, PMOS, your gain is always like 10 or 15, pretty low. But with a differential circuit, you'll see how high the gains are, right? Differentially input signals, you can get pretty high gains like this. Okay, now if an RL of value equal to RO is connected, if RL and RO are equal, that means the output resistance of the amplifier equals to the load resistance, then AD with the load is just GM into RO parallel with RL, and if they are equal, then the factor of 2 is what you get. That means with the load is half of without the load. So RL, if it is equal to RO, which is 75K, then you get a half of the total gain. Okay, so remember that condition. I think we have studied this in the past, but it's an important rule that we use quite often. Okay, so that was problem 891, and so these are all the problems I have on the MOS pair with the active source, active loaded. There are some homework problems also. Please do those by yourself. That will help you improve your understanding of all this matter. Okay. All right. Next, we come to the BJT. Like I said, I don't. You're not going to get too many questions on BJT related stuff in the quizzes, etc. on the exam. Maybe I'll have a question in the short, short form questions. Remember, in my quizzes, I have question 1 is always a collection of short questions, of 5 short questions. I may sneak in a BJT related item in there, but generally I'm not going to give you a full problem to solve on BJTs. Okay, that's what generally we are doing at NAU, so I don't want to break the rule, but I might give you like a short question. Okay, so 817 is again an exercise related to BJT differential amplifiers with active load. So mostly, other than the fact that you get a mention of beta, there's pretty much zero difference. Well, ACM has a slightly different formula, which of course involves beta. But other than that, most of almost everything, um, and of course there is always a input resistance calculation, which for BJTs is, I mean for MOS, it's considered infinity, right? Because no current flows in the gate. Here current does flow in the base, so there is an input resistance of finite value, of definite value. Otherwise, I feel everything else pretty much is similar. Instead of calling it ID or I drain, we call it IC or I collector. And we still use I collector as half of bias current I. So you should not find anything too different between MOS and BJTs in this case. Alright, so 817, the answers are here, but let's make sure we solve it and get it. 817 is on page 6. Alright, starting with GM. GM is again small gm12, which is IC by 2, collector current by 2, Vt, and collector current is, oh, it should be I by 2, not IC by 2. Yeah, mistake. So this is I by 2, okay? Jeez. Huh, it looks like half, right? Okay, hopefully that will help you. But if you're listening to the lecture, you'll not make the mistake. Okay, I by 2, which is 0.4. Vt is the thermal temperature. Make sure you understand this. This is not the threshold voltage. This is a thermal voltage, not thermal temperature. Vt, when we are talking about BJTs, is the something called the thermal voltage, which we studied way back about, and it's generally 0.025 volts or 225 millivolts. So make sure you put that right thing in here in the denominator. So that comes out to be 16. RO is the parallel combination of RO2 and RO4. Each of these is VA by IC, which is VA by I by 2. Here I have the right I by 2. Here I messed up by putting the IC, which is 100 by 0.4, which is 250K. So RO gives you 250K in parallel with 250K, 125. AD is GMRO, GM 16 milliamps, RO 125 kilo, so you get 2000 volts per volt. So you'll also notice that compared to MOS amplifiers, the gain numbers seem even higher when you are talking about BJTs. That's an important difference. Okay, our input resistance of the differential of the input signal VID applied differentially to the two bases, the input resistance is this formula 2 beta by GM12, and beta is given, GM12 we calculated, so you get an input resistance of 20K. Our EE, which is this resistance of this whole source, current source, is VA by I, which is 100 by this, so 125K. So A common mode gain is RO4 by beta 3 of this transistor. It's important to see which transistor we are talking about. And REE. Okay, so that comes out to be 0.125 CMRR. And again, I made a mistake. This should have an, does this have a negative value? Yeah, it should have a negative value. Yep, ACM should have a negative value. So I keep missing that, but I don't want you to miss it. There should be a negative sign, so this is minus 0.125. And so CMRR, when you take the absolute values, comes out to be 160,000 or 104 dB. So generally for BJT differentials, the CMRRs are even higher, like 100 dB and above. Okay. All right. So that was this problem on page 68. All the formulas are here. Yeah, here there is a negative sign for the ACM. Important. 893, similar amplifier. I is 500 microamps. VA is given to be 10 volts all across the board, and beta everywhere is 100. So find differential input resistance, output resistance, short circuit transconductance, which is the capital GM, open circuit voltage gain, yeah, A0, which is AD really. Open circuit meaning no load resistance, right, which is AD. What would be the voltage gain if the input resistance of the subsequent stage is equal to RID of the stage? So RID of this stage equals the input resistance of the next stage, right? So that's what's being asked. All right, so let's see how to solve this. It's a pretty straightforward problem, 893. Start with IE1, IE2, which is similar to IC1, IC2. We are neglecting alpha here. So it comes out to 0.25 milliamps. GM12 is IC12 divided by V thermal, which is 10. RO is VA by IC, it's 40. RID, that's the input resistance of this differential amplifier, is this. The R output is also this. GM and AD you can find like this, 200 volts per volt. GE voltage gain given RL equals RID equals 20. So I guess the point is making is the input resistance of the next stage is the same as the input resistance of this stage, which are both 20K. If that's the case, then what is the uh, voltage gain? You can do this, the voltage gain divided by or multiplied by RL plus RO, or you can take the same approach that we used previously. Well, I guess this is the right way to do it. The overall gain, and what does he call it? What will be the voltage gain if the input resistance of the subsequent stage is equal to RID of this stage, right? So that RL is equals RID. So your overall voltage gain is modified in this way, 20 by 20 plus 20, which is 40. So the gain fell by a factor of 2. which is, I think, similar to what we did. Yeah, here also we had a gain, and we were asked to say, what if the gain falls by a factor of 2? And we came up with a value of the resistance for RL, which is identical to the value of the output resistance, right? So it's a similar approach. Both approaches should work. Okay. I have 2 more problems, I think. I don't have time to do them, so I will let you look through them. They're pretty straightforward, pretty much uh, same thing as what we just did. Not too many surprises. Here, I thought there's an interesting way to find the bias current I, because this kind of circuit is given, but you can see how I did the math. Okay, all right, that's it. Sorry, I'm going over just a couple minutes, but with that we finish part C of this chapter.